In 5.10, we're going to introduce optimization. Optimization is one of the most useful applications of calculus that is not just used in engineering, but is also used in business a lot. Okay, we're just going to set up the problem and not actually solve the problem today. We will solve it the next day, which means we're going to do steps 1 through 3. Okay, optimization means given certain restraints, you're trying to make some value the most maximum or the most minimum, depending on if you're trying to save money or not save money, depending on the situation. So we're going to draw a picture. If it's applicable, identify known and unknown quantities, write an equation that will be optimized, and then write your equation in terms of a single variable. After that, we will pause and finish next class. Okay, so we're going to write the equation to be optimized in one variable. Okay, what do they tell me? Find two numbers whose sum is 30 and whose product is as large as possible. So what we're actually going to optimize when we do this for real, we want the product as large as possible, so we're going to have to find a maximum product, which we're not doing today, but we will be next time. And remember, maximum and minimum is what we've been doing this whole chapter. Okay, let's set up an equation first. Okay, what do they want? Two numbers whose sum is 30 and their product is as maximum as possible. So I'm trying to maximize the product. Let's see, product is when you multiply two numbers, so let's make them x times y. Okay, so I already wrote an equation to be optimized, and that's my product equation. I need to write my equation in terms of a single variable. Right now it has an x and a y in it. I would prefer if it just had an x or a y. So let me use the other piece of information they gave me. They told me that the two numbers whose sum is 30. So they are telling me that x plus y is 30. So I can solve for x or y in terms of the other one. Let's solve for y. Okay, which means y equals 30 minus x. So let me substitute back that back into my product equation, which is what I'm trying to maximize. So I can rewrite this as x times 30 minus x. Okay, now I wrote the equation in terms of a single variable, so I'm going to stop here. Next class, we will determine the desired maximum value using calculus techniques, which means take the derivative of critical numbers, figure out which one's the maximum. But for right now, we're just going to set it up. Okay, let's look at the next one. Okay, they've already given me a graph. What point on y equals the square root of x, which is this function, is closest to 5, 0? Okay, so what am I trying to do? I'm trying to figure out a point somewhere on y equals root x, maybe like right here, such that this distance is the smallest possible. So I'm going to try to find the minimum distance value. Okay, first, how do I find the distance? Distance formula, if we remember that, let's just write that out for now and then think about it. Is when you subtract the x's and you square it, you subtract the y's and you square it or something like that. Okay, now let me look at the information I have and see what I can plug in. Well, I know that one of the points is 5, 0, and that's fixed because they want it to be going from 5 to 0. Now the second point here is x comma y, and I'm trying to determine which x, y is the closest. But actually, they're telling me that y is root x. So instead of writing x comma y, I could write x comma root x. That way I at least have one variable. Okay, let me plug this in and then stare at my equation. Okay, x2 minus x1. Let's just do x minus 5. And then in the other way, I have root x minus 0 squared. And it could be vice versa. Distance formula, it gets squared anyways. Let me simplify this a little. I don't mind the x minus 5 squared. Okay, but if I do square root of x minus 0, I get the square root of x. And the square root of x squared is just x. So how is this looking? I'm trying to minimize the distance, and I have everything in terms of x. Okay, so I'm going to stop here. I'm trying to minimize the distance, and I have only one variable here. And then if I wanted to find the minimum, I could take the derivative, find the critical points, figure out which one is a minimum. Okay, let's look at number 3. Okay, let's consider this next one. It says Mr. V needs an open-topped box, not boxed, to store his Pokemon cards. He has a piece of cardboard that is 14 by 30 inches. He will cut equal-sized squares from each corner so that the 4 sides can be bent upwards. What size should the squares be cut to create a box with the largest volume? Okay, let's start out with this piece of cardboard. Here is his piece of cardboard. Okay, it's 30 inches by 14 inches. Okay, he wants to cut squares out of the corners, equal squares. And then after he cuts out the squares, he can fold up each of these rectangles on the sides to make an open-topped box. Okay, let's give a dimension. These are equal size squares, so they're all size X. Okay, now what are we trying to optimize here? He wants the largest volume, so we're going to find the maximum volume. But let me think volume here. So this is a box, rectangular prism, so we'll go with length times width times height. Okay, let's consider this. What is the length of this box? Well, depending on your perspective on length, let's go with this one. The entire length of this cardboard is 14, but he's going to cut out this little x and this little x. So the length, we're going to go with 14 minus the x and the x minus 2x. That's from here to here. Okay, now he's going to go to the other side, and then once he folds up his little box, the base is actually only going to be, actually I should put that dot in here. Let me put this line here. Okay, once he folds it up, this is like the edge of the width of the base, which is going to be, it was 30, but then he cut out the 2 x's on each side, so now it's 30 minus 2x. Okay, now once he folds up the corners, like this little thing gets folded up, this is going to be the height of the box. So the height of the box is only x. Okay, now this is what I'm trying to optimize. I could leave it like this, but in the next section, we're going to actually have to find the derivative. So let's multiply this out just for the fun of it. Oh, geez, 14 times 30 is 420 minus 28x minus 60x plus 4x squared, and then times that extra x. Okay, so this is going to be 420x minus 28x minus 60x negative 88x times that extra x plus 4x to the third. So this is going to be the volume equation that I'm going to find the derivative of, and then I'm going to try to optimize it and find the maximum volume. Okay, let's try to set up one more. Okay, 2 towers are 30 feet apart. Okay, here's my tower. Doesn't actually have to be a tower. Here's my other tower. Okay, I know that the entire distance across is 30 feet. Okay, one of them is 12 feet high, one is 28 feet high. Let's give the shorty a 12 and the tallie a 28. Okay, there's a stake in the ground between the 2 towers. The top of each tower has a wire tied to it that connects to the stake in the ground. Where should the stake be placed to use the least amount of wire? Okay, so there's a stake in the ground somewhere, and there's a wire and a wire. Okay, my wire is the blue pieces. I'm trying to least amount of wire. I'm trying to minimize the wire. So the wire is those 2 little pieces. Let's just give them some letters. How about W equals Y plus Z? Okay, now do I know what Y and Z are? I see it looks like a Pythagorean theorem problem. Let me put a right angle here because the towers are standing upright. Okay, I know that this is 28. If I knew this side, I could easily find Y using the Pythagorean theorem. I don't know this piece, but I do know the entire section here is 30. So let's go ahead and just call this side of the triangle x. Now, if this piece is x and the entire distance is 30, if I wanted to get this distance, I would just do 30 and subtract whatever this distance is, whether it's 10, 30 minus 10, 20, something like that. So I'm going to call this 30 minus x. I could have easily done this the opposite way because it doesn't make a difference. Okay, now let me see if I can rewrite this now. Okay, now this means that y is going to be the square root of this squared plus this squared based on Pythagorean theorem. Let me write this out real quick. I'm not good at mental math. Okay, so y is going to be the square root of w squared plus 28 squared. Okay, now what about z? Okay, z is going to be 30 minus x squared plus 12 squared. Okay, and then I'm going to go ahead and square root both sides. X. Okay, now will this do? Let's see. I wrote w in terms of, why did I put a w there? What is that supposed to be, an x? That's supposed to be an x. Okay, w is now in terms of x. Let's check. I'm trying to minimize w. W equals the square root of x squared plus 28 squared plus the square root of 30 minus x squared plus 144. Okay, now I could simplify it, but I could find the derivative of this. I know how to find the derivative of this, and I can do so tomorrow.